Okay, some informal diagnostics using residuals. If you think back with me to the beginning of this module when we looked at the simple linear regression model, the statement, there was 4 assumptions there. The first assumption was that we had a linear model, and then the last 3 assumptions dealt with the theoretical error terms. That is, that the error terms are normally distributed, that they have a constant variance, and that they are independent of each other. And those assumptions need to be valid or somewhat close, reasonable, based on the data in order to do any inference, i.e. Confidence interval on the slope, hypothesis test on the slope, this sort of thing, in order for those inferences to be valid. Okay, so we need a way to check out our assumptions. All right, and we're going to look here. We're going to work through the residuals. So if you recall the residuals here, the ith residual is the response value minus the fitted value. Okay, that was the residual. And so we have a residual for every data pair, and that in some sense allows us to look at assumptions on the underlying error term. Now, the first assumption with our simple linear regression model is that we have that x and y are linearly related. Well, one way to check this out is to check to see if you have the departure of nonlinearity, is to look at, one way to check this out is to look at the scatter plot. Okay, so the scatter plot, we know what that is. That's just the plot of y versus x. And looking at the pattern there, if it looks linear, then that assumption seems reasonable. If you see something that is, if the scatter plot is nonlinear, then you've got some issues there. Perhaps you want a different sort of model. Perhaps you want to transform the data. We won't get into that very much in this class, really, if at all. But that is something that could be done. You look at the scatter plot. That's one thing you could look at. Or you could look at what's called the residual plot. And there's several residual plots out there, but the one I have in mind here was to plot x or y hat versus the residuals. And what you want to see is you want to see a random scatter around 0. So this would be good. And if you saw a pattern, so something like this, so again, here's our residuals, we're plotting our residuals, here's 0. If you saw a pattern that was something like this, so that's a clear sort of pattern, that the residuals were negative, then positive, then negative, that would indicate that our model is perhaps the wrong model, that we should not be using a straight line to fit the scatter plot there. Okay, so let me X that out. The other departure we could have would be a non-constant error variance. Let me back up just to be clear. This would be bad. So patterns are bad. We don't want that. The second assumption that we're going to consider here is the constant variance assumption. And again, we're going to look at a residual plot. We're going to look at x or y hat. You could plot either one of those on the horizontal axis versus the residuals again. And again, you want to see a random scatter. This is ideal. And it kind of makes sense if you're looking to see if the variance is constant across all pairs of data. If you would look to see if the spread is roughly the same moving across here from left to right for X or for Y hat. Now that would be ideal, but sometimes it is common enough to see a flare. You might see a flaring out where at first the residuals are kind of small, but then as X increases the residuals get bigger, and that would reflect that there's a problem with the constant variance assumption in the error terms. The error terms being independent is another assumption, and we look here at this residual plot. It's slightly different. We're going to look at the residual plot where we're plotting the residuals versus the observation number or really the time. If the data comes in terms of the pairs are recorded over time, you would want to start from the earliest and go to the latest. And generally, if you see patterns here, patterns are bad. It might indicate a lack of independence. Lastly here, looking at normality. Several things you could look at to check for normality. You could look at the histogram of the residuals. You could look at the box plot of the residuals. What I really like though is the QQ plot of the residuals. So I would prefer this over the other two. The other two, histogram and box plot, and to a smaller extent the QQ plot, the information they yield about the shape of the underlying population there's less information in it as the sample size is small to moderate. And so the QQ plot helps out somewhat in this problem area or potential problem area. So I recommend that you use a QQ plot to check for normality. Okay. Here is a Sparrow example in JUMP, or some output from JUMP. You'll want to see the JUMP demonstration to check out how you get these plots and how do you do simple linear regression and JUMP. But if you look here at the outputs, this is the residual versus the predicted values, the days predicted. And if you look here, there seems to be for practical purposes, for all intents and purposes, a random scatter about 0. And so this plot, if we're using residual versus the predicted value, it would indicate that linearity is appropriate, or that let me back up. It would indicate that the linearity assumption and the constant variance assumption are appropriate. Okay, because we have this random scatter. This plot here is the Y hat versus the Y plot. It's another plot you can look at. if the model fits the data pretty well, then your y's and your y hats should be pretty close, and so they should be pretty close on a line there, and that's what we see with this particular plot. This third plot here, residual by the row plot, it's the residual by the row number there, and this indicates that we don't really see a pattern here, but that that the independence assumption would be reasonable here. Okay, and then lastly here, this is a QQ plot. So it's got the residual versus the normal quantile. This QQ plot is slightly different than the kind of QQ plot that we've worked with before, but it's the same idea. The principle's the same. If the plot is close to linear, then normality is tenable. Now we kind of interesting here. We see this S shape in the QQ plot, and that that might be cause for investigating further the departure from normality. If we were in a regression class, we would talk about ways to try to remedy this problem. But for us, I just want you to know you do need to check these assumptions, or they need to be checked by somebody in order for statistical inference to be appropriate in the simple linear regression setting. But just right here for this last plot, the QQ plot indicates there may be a problem with the normality assumption. Okay, so we want to be aware of that. Again, for us in this class, I don't want you to I'm not interested in you becoming really proficient in regression, but just being aware of the basic model, basic inference procedures, and the basic assumptions and how you can check those. Because you may read a applied statistics paper in a medical journal, in a business journal, in an ag journal, or in a nursing journal, and they use regression analysis, and it's good to know when they talk about a coefficient of determination, when they talk about a correlation, when they talk about a t-test, what are they referencing? And hopefully this module gives you some insight into that.